Okay, let's move back now to our familiar set of scores. Let's say we're using a protocol of some sort to score children's level of aggressive behavior. The scale is a 7-point scale in which we'll assess each child in an elementary school class. We did our observations. Here are our results. On the left-hand side is the raw data, and on the right-hand side here is a frequency table showing the number of children who scored in each different level. We can look at the same set of scores in a histogram in addition to looking at it in a frequency table. If we were to select a case at random, what's the probability that the case that we select would be one where the observer scored the child a 2? Well, you can take a look at that. There are a total of 9 scores. Only one child scored a 2. So the probability, it's very similar to our dice example, the probability is 1 out of 9. What about the probability that a child scored a 3? Well, you can see that there are 2 children who scored a 3, so the probability there would be 2 out of 9. I've illustrated those probabilities over here. You can see that the probability of selecting a child who scored a 4 is 3 out of 9, since there are 3 children who scored a 4, and we have a total of 9 cases, so 3 over 9. What about the probability of selecting a case where a score falls below a 4? How would we figure something like that out? Well, it would be the sum of the number of children who scored a 2, one child, and the number of children who scored a 3, or 2 children. So the number of children who scored below a 4, just to follow our addition rule, 1/9 plus 2/9 equals 3/9, or a probability, or if you prefer, a proportion of 0.333. Okay, let's take a look at another one. How about the probability of picking a child who scored a 4 or above? So in the previous example, we had below a 4. Here we have a 4 or above a 4. And I'm sure you can do this very quickly just by looking at it. We have 3 over 9 plus 2 over 9 plus 1 over 9, yielding a probability of 2/3 or 0.667. And we'll do another one. How about the probability of selecting a child who scored either a 4 or a 5? And again, the answer is very simple. These basic principles are the same regardless of how large a sample we draw. Although I made up the previous example, many of the things we study have a similar bell-shaped distribution. Most of the observations cluster around the mean, and the further away from the mean a score is, the less likely it is. In a normal distribution, what's the relationship between a mean and a median? They're the same. So half the scores will be above the mean and half the scores will be below the mean. Let's say we're looking at a set of SAT scores. The mean SAT score is 1,000. It's actually a bit higher than that. But just as we did in the simple example before, we should be able to determine the proportion of students who got a score of, say, below 800. And that's illustrated here in this histogram. We can simply count up the number of bars and the number of cases in each bar. And I've estimated here that that about 15% of the students who took the SAT wound up getting a score of 800 or below. Now this works fine when you have a discrete set of categories. But what if we're interested in something more precise? What if we're interested in something that's measured on a continuous scale? A continuous scale is what again? It's a scale where there's an infinite number of possible values between any two values. So your height, for example, is measured on a continuous scale, because although we may not have a ruler that measures down to the level of nanometers, in principle such a measurement is possible. The number of children you have, on the other hand, is something that would be measured on a discrete scale, since you can't have any fractional children. You either have no children, one child, or two children. You can't have 1.5 children. So if we had to measure on a continuous scale and put together a similar histogram, it would look something like this. The vertical axis shows the number of observations at each point. The horizontal axis shows the score. And for a variety of reasons, we're going to display these scores as z-scores. So far, so good. If you followed along, I don't think there's anything here to cause you a problem. But how do we find this red shaded area on a histogram such as this one? Unlike the case with discrete data, we can't just count the number of scores in each category. In other words, there are no categories because the distribution is continuous. Since we've labeled the x-axis using units of standard deviation, let's start out by determining the percentage of scores one standard deviation below the mean. Remember, we can express this either as a percentage of scores or as the probability that a score will fall below one standard deviation less than the mean. One of the really interesting properties of the normal distribution is that it can be shown that about 34% of the scores will fall between the mean and one standard deviation below the mean. Because the distribution is symmetrical, we can also see that 34.1% of the scores will fall between the mean and one standard deviation above the mean. Also, because the distribution is symmetrical, half the scores will fall above the mean and half the scores will fall below the mean. So combining what we know so far, that 34% of the scores will fall between one standard deviation below the mean, and that half the scores are above the mean, we can determine now that the total area that we've highlighted, one standard deviation below the mean, is about 15.9%. 84.1% would be the proportion of score, or the probability of scoring more than one standard deviation below the mean. I know that the more and the above and the below and the negative and the positive can get confusing, but if you look at the graph and understand that the distribution is symmetrical, you shouldn't have too much trouble understanding this.
We can also show that 47.7% of the scores will fall between the mean and 2 units of standard deviation above or below the mean. This leaves 2.3% in each of the tails beyond 2 standard deviations from the mean. Similarly, it can be shown that 49.9% of scores are within 3 standard deviations of the mean, leaving only a tiny 0.2 of 1% in each of the tails. But let's tackle now a somewhat more difficult problem. Knowing what you know so far, can you compute the percentage of scores that are greater than 1 standard deviation below the mean and less than 2 standard deviations above the mean? That would be this green area in here. The area 1 standard deviation below the mean, and this area 2 standard deviations above the mean. If we add these two together, you can see that the sum of these two areas is 81.9%. So we can say that 81.9% of the scores fall between 1 standard deviation below the mean and 2 standard deviations above the mean. Let's just summarize this, because with these rules we can figure out a number of different problems. The probability that a score will be within 1 standard deviation of the mean is 34.1%. The probability that a score will be within 2 standard deviations of the mean is 47.7%. And the probability that a score will be 3 standard deviations above or below the mean is 49.8%. Also important to bear in mind that the total area above or below the mean is 50%. Or a probability of 0.5. Well, this is all well and good, but what do we do when we're asked, say, the percentage of scores that are above some fractional z-score? Or again, what's the probability that a score is above or below a particular z-score? The problem, in other words, looks something like this. The proportions on the last slide were computed using calculus and a very frightening formula. Fortunately, a computer or even your phone can determine these proportions for you if you convert a given raw score to a z-score. There are a number of online calculators available to do this, and I happen to like this one. You can go ahead and click the link, But just bear in mind that this formula does not require you to compute z-scores. If you enter the mean and the standard deviation of the raw scores, it will convert them to z-scores in the background for you. We're looking for the probability of getting a score in this problem, or the problem in the previous slide, I should say. We're looking at the probability of getting a score greater than z equals 0.22. So you have to tell the calculator what the mean of the distribution is. It would be 0 if you converted things to z-scores, and what the standard deviation of the distribution would be. Again, if you convert it to z-scores, that would be 1, since these are the mean and standard deviation for every z distribution. And after the video is over, you should try other z-scores just to get an idea of how the calculator works. Now, on an exam, you can't use the calculator. That's just college policy. You have to use a table to look up these probabilities. We'll be covering how to use such a table in another video. But for now, let's just summarize where we are at this point. With the information that you have, you should be able to solve any kind of problem that involves figuring out the proportions of scores above or below a given value or between two values. Here are the steps. You compute the mean of the distribution. Use the mean to compute the standard deviation, and then using the mean and the standard deviation to find the z-scores for the raw score you're interested in. I'll just say parenthetically, in most of the problems you'll see in this class, step 1 and step 2 have already been done for you, and you'll have a mean and you'll have a standard deviation given in the problem. With that mean and standard deviation, as I just said, you're going to compute a z-score. Now, this is very important. Draw the distribution labeling the mean and the z-score you just computed, and draw a set of arrows to show what part of the distribution you're interested in. What is the area under the curve that you're going to be looking at, that you're going to be trying to find on the table? And then compute the area under the normal table, or I should simply say look up the area under the normal table, under the normal distribution, using the tables or one of the calculators. Hope that you found this useful, and stay tuned for our video about how to use the z-table.